Ladies and gentlemen, we're joined today by Professor Geraint Lewis. Geraint, thank you for coming on the show. Appreciate your time. How you doing, mate?
I'm good, thank you. How are you?
Yeah, I'm doing very well. I understand you're from Wales, yeah?
Yes, originally I was born and raised there.
Yeah, right. How'd you end up
Yeah.
in Sydney? What brought you over
Um,
here?
well, job mainly. I started working for the Anglo-Australian Observatory back in 2000. So that was only going to be like a 5-year position, and I thought I would be heading overseas again. I'd already spent time in the US and Canada, but there was a position come up at the University of Sydney, which I applied for, and I've been there now for 23 years. So yeah, I wasn't planned, but an opportunity came up, and so I took it.
Yeah, love it. You love it here?
Oh yes, yes. I mean, it's been a great place to raise my kids. My kids are now adults, and yeah, I think it's been really, really good for them. Better than it would have been, I think, if we'd stayed in Britain or something. So yeah, I very much like it here. And considering that the rest of the world seems to be falling apart, it's good to be a long way away from anywhere.
What'd you find the US like?
Look, I visited the US
And
recently.
Canada.
Oh,
Talk about falling apart. Canada at the moment.
yeah. Well, look, I really enjoyed living there. I mean, there were
Yeah.
good places to live, and I definitely liked the wilds of Canada. I was in British Columbia, and just the mountains and the scenery, etc. It was all really good. But because I was only on sort of short-term positions there, I didn't have to worry about the big political issues that were going on. I was younger then, so I didn't think about politics that much anyway. So
Yeah, right. Yeah. Look, I don't know if you're aware. Well, first of all, you're a cosmologist?
yes.
Right. So, can you explain to both myself and the viewers what is actually the difference between a cosmologist and an astrophysicist?
Okay, so there's no real difference here. It's really to do with umbrella terms for capturing things, right? So in the strictest sense of the word, an astrophysicist is somebody who applies the laws of physics to understanding something going on in the universe. So I might want to understand how stars work or how giant black holes work or something. So a subset of the whole astrophysics sort of thing is cosmology. And cosmology is the sort of study of the universe as a whole. How does the universe operate in terms of where did it come from and where's it going? So we sit within astrophysics, but our view is essentially trying to cover everything that's going on in a coherent way.
Yeah. Righto. So, with how the universe started and where it's going, do you think we have a better idea on that? Like, do you think we have a better understanding of how the universe started and how the universe is going to end, as opposed to, say, I don't know, 15, 20 years ago, even more?
Oh yeah. Look, things have changed a lot. So firstly, I should point out that like our modern vision of the universe is now about 100 years old, right? So
Yeah.
people like Einstein and Hubble working back in the 20s and 30s. Over that time period, over that last 100 years, we've collected a huge amount of data, and especially as our telescopes have gotten bigger, we've been able to peer deeper and deeper into the universe. And so our picture has been getting more and more refined. So we now sort of know that we live in an expanding universe, which was one of the big shocks that came along in the late 1920s, early 1930s, that the universe had a beginning, right? Up until that point, many people thought the universe had been around forever, but those observations showed that there was a start, and we now can date that start to like almost 14 billion years ago. And we've been able to trace the way that the universe has evolved over those 14 billion years. We know that it's expanding, it's getting cooler, it's going from a very simple state where everything was sort of smoothly distributed into a more sort of complex state where we have stars and galaxies, etc. And we can use our laws of physics then to essentially play the tape forward, ask what's going to happen to the universe tomorrow, in 1 billion years, in 1 trillion years, etc., etc. So we do have a much better idea about how the universe operates to what we did decades ago. But in all of science, there's also uncertainty because we know that we don't know everything, right? So we are finding out new things about the universe all the time, and that might change the way that the universe basically actually behaves into the future. So we have a pretty good idea, and but with every new scientific discovery comes the possibility that we'd have to refine our ideas in the future.
I think the whole unknown of the universe is what is so interesting about it.
I agree. I mean, this is part of the reason why I am a cosmologist, right? I have a particular sort of focus, the area I like to work on, which is known as the dark side of the universe, right? So we know that our universe contains different kinds of mass and energy. And what we've discovered again in the last 100 years is that the dominant form of mass is this stuff that we label as dark matter. And
Yeah.
at the turn of the century, we essentially discovered that the dominant energy in the universe is this stuff that we label as dark energy because we're not very imaginative, and we know these things dominate the universe, but we do not know what they are. Right? So there's a big mystery there to, what is this stuff that's out there? And how is it related? Or is it related to each other? Or what does it mean for the evolution of the universe, etc.? So, yeah, it's the mystery, it's the why questions that keep not just me, but other scientists, coming in every day and doing the science, is because there are always more questions to answer.
Dark matter, dark energy, somewhat similar to black holes. I might be wrong here, but is that something that we kind of theorized before we actually knew what it was? Like we assumed it was there before we even had realized it. Like, do you know what I'm saying?
I'll say yes and no. So
Right.
so dark matter has been around since the 1930s, but really it was the 1970s where we got the observational evidence that really confirmed there was something going on. So people before that point had suggested there might be other stuff out there that doesn't emit light, doesn't emit radio waves that we can't see. But it was like a curiosity more than anything. And so the discovery of dark matter as a discovery was a bit of a shock, but not as big as a shock as the discovery of dark energy at the end of the 20th century. So Einstein had sort of theorized about the existence of something equivalent to dark energy called the cosmological constant way back in the 1910s. But once he discovered that we live in an expanding universe, he thought, I don't need that term and I'll just throw it away again. But at the end of the 2000s, it came back with a vengeance, right? The thing that Einstein had suggested. So people hadn't really theorized in the sense that they'd said, we expect this stuff to be out there, let's go looking for it. What they had done is they were doing their experiments and they were getting results that they didn't quite understand. And they realized that they had to add these ingredients to explain our observations.
Yeah, right. Yeah, wow, that's fascinating. Look, you talk about an expanding universe. Okay, I've got a question for you. So my understanding is the universe is expanding like a balloon. Yeah? So how do we have things like the Milky Way and the Andromeda Galaxy colliding one day if everything's expanding?
Okay, so we'll do two things here. So number one is we'll have to remember that balloon picture is an analogy, right? So expanding space, I can talk about it in terms of the mathematics. It looks a bit like a balloon, but it's not a balloon. Now, the thing is that if you want to think about it as the expanding balloon and you've got your galaxies, let's say you put like, let's put, we don't have 1 cent in Australia, 5 cent pieces on the balloon, right? And as you said, as you blow up the balloon, you expect that the distances between all of those objects to increase. So how come Andromeda is heading towards us? Well, what you have to remember is that in the universe, there are two competing forces at work effectively, right? And forces in air quote here. Number one is the expansion, which is trying to pull everything apart. And number two is gravity, which is trying to pull everything together. Okay.
Right.
And
So let me add something there, right? So you're saying gravity is part of it. Gravity's pulling things together. That's how we orbit our sun, yeah?
yeah.
How is the moon moving further away from the Earth? Isn't the gravity of the Earth pulling the moon towards us?
Yes, but okay. So there's two things. Number one.
Yeah.
Yes. The moon, the gravity between the Earth and the moon is pulling the moon towards the Earth, right?
Yeah.
But the situation that you have to think about with the moon is it's the same as if you've got a ball on a string and you're whizzing it around your head. Okay, so you're applying a force that's pulling the moon towards you, and that's holding the ball in its circular motion, right? So that it's exactly the same thing for the moon. Now the thing is that you mentioned that the moon is moving away from us, and it is moving away relatively slowly, centimeters per year, kind of thing.
Yeah.
And that's because the moon and the Earth aren't perfect spheres. Right? We know that the Earth bulges at the equator and the moon bulges slightly as well. In fact, the moon is slightly more complicated. And that means that you've got additional gravitational interactions between the Earth and the moon. And that means is that the moon is essentially, the force acting on it is not perfect in holding it in that circular orbit, but it's actually, there's a weakening, and the moon is actually moving away very slightly away from us. Okay, so gravity works, right? Let's be clear here that we've understood how the moon works since Isaac Newton in the 1600s. So there's no issue around that. So, but when it comes to the Milky Way and Andromeda, right? If you think about it, they're two nearby galaxies. So they're 2 million light years apart. And that's actually close, cosmologically speaking. So in our little patch of the universe, the gravity between those dominates, and they're being pulled together. But if we look at galaxies further away, we see that they are moving away from us. Those ones, the expansion is winning over the attraction of the Milky Way and Andromeda. And I can give you another example, which I think is kind of cool, is that the Milky Way and Andromeda are part of a collection of galaxies called the Local Group. They're the two biggest galaxies in there. There's lots of others. And the Local
Milky
Group
Way
itself
is one of the biggest in there as well?
Yeah. So Andromeda and Milky Way are the two biggest. Then there's another one called M33 Triangulum. And then there's about 100 small galaxies in there. And that
100?
Yeah. These are called dwarf galaxies. They're quite small. But the entire thing is falling into what's known as the Virgo cluster. So the Virgo cluster is thousands of galaxies, so lots and lots of mass there, and it has grabbed hold of the Local Group, and the Local Group is falling towards Virgo. But the way that dark energy is acting, that rate of us falling in is slowing. We will stop, and then we will move away again, because eventually the expansion of space will dominate in that interaction. So it's all a play between things basically being pushed apart and other things trying to be pulled together by the action of gravity that gives you the overall effect that we have in the universe.
Yeah, well, that's crazy. Okay, it's hard to wrap my head around. Difficult to wrap my head around it. So in a way, are we all the galaxies inside the Local Group? They're kind of falling into each other in a way, but they're kind of like
essentially, yeah. So in the Local Group, the local gravity dominates, and in fact, what we have got is that we have the Milky Way galaxy here, we got Andromeda here, and most of those little galaxies actually orbit the big galaxies, and some of them get a bit too close. So if you take like the Milky Way, it's a big galaxy, but these dwarf galaxies are small in comparison. And if they get too close, then the gravity of the Milky Way can tear the smaller galaxies apart. So our Milky Way has gotten to be so big by being a bit of a bully, and it consumes smaller galaxies that it tears apart. And at the moment it's tearing apart one which is known as the Sagittarius dwarf galaxy. That's basically being dismembered. But another one which is being torn apart very steadily is the Magellanic Clouds. So the Magellanic Clouds, your listeners might actually know them. You go out on a nice dark night get away from city lights, you can see the Magellanic Clouds. They are two small galaxies which are orbiting in the Milky Way, but over the next, few billion years, they'll be torn apart and shredded and will eventually disappear from the sky.
So to make it clear, the Andromeda Galaxy is the one bullying us when we get to that point, yeah? Because the Andromeda Galaxy is much bigger, yeah?
No, it's not much bigger. It's only a couple of times bigger. So Andromeda is bigger than the Milky Way, but when those two galaxies meet, it's more of a train crash, right? Because they're equal sized. Okay, so it's more like a prize fight between two seemingly equally matched people. And what will actually happen in that collision, which is probably around 4 billion years from now, 3 to 4 billion years, in that collision, the two big galaxies will essentially tear each other apart. So they will come in, and they're basically it's more of a wrestling match than anything. The gravity of each reaches out and grabs the other and starts to pull on them, and the spiral discs, the beautiful spiral discs that define the Milky Way and Andromeda, they get ripped apart, but then the cores of the galaxies crash together, and eventually, if we give it like 7-8 billion years to let everything settle down, there will be a galaxy left over, right? There'll be a remnant of the collision, but it will be a mess. It won't look beautiful. It won't look like a spiral galaxy. It won't look like Andromeda is now. It'll just be a fuzzy ball of stars. And we see lots of these fuzzy balls of stars out there. We know these collisions have occurred in the past. But yeah, that's where it's heading for, is that eventually our local group will be dominated by just the remnants of the galaxies that are here now.
Yeah, wow. Look, there's something I'm very excited to talk to you about. Now, I don't know how much you've been following this type of shit compared to me, but look, do you know much about K2-18b?
Yes. Well, I wouldn't say I know a lot about it, but I do know what it is.
Okay, so look, that keeps me up at night. I love that shit. K2-18b, we've discovered DMS, which is a biosignature. It's an element only produced by life, right? And this is the strongest evidence of life so far, like ever in history. This is crazy to me.
Okay. So I'm not planning to rain on any parades here, right?
No, don't do it to me.
No. Oh, no. Okay. So look, firstly, of course, it is a sterling effort to go out hunting for, they call them biosignatures. Are there signatures in the atmospheres of other planets that can reveal the presence of life? Now, the problem that we have is that these observations are hard, right? So we're having to use James Webb, the biggest telescope in space, parked out, really cold, so we can look and get the light from these planetary atmospheres. So the thing is that you read the headline in the newspaper, right? Woo! Biomarker found in planet, and I know how exciting it gets, but then you have to go and read the paper, right? So, for me, there's the headline story, but then there's the scientific paper. And the scientific paper is a lot less certain than the news article, right? And we could, if you wanted to, we could get into a discussion on statistics and sigmas and Bayes factors and all this kind of stuff. But I can tell you that I think there's two key things here. Number one, that how confident that they are that signature is there is really not that confident. I.e., it would be a bit of an outsider in the Melbourne Cup kind of thing, right? So you put a couple of bucks on it because you think, it might be right. But as yet, I think most people that look at the data sort of go, I'm not overly convinced by what you're telling me that I'm seeing here. The other thing is, which I think also the press doesn't like to hear, is that we don't have unique biosignatures, right? We talk about, I think it was dimethyl sulfide, I think that was what the DMS stands for.
Dimethyl sulfide, yeah.
Yeah. That on Earth, that is a consequence of life, right? Fair enough. That's the primary source of this stuff. But we don't understand the chemistry on other planets, right? We don't understand if there's not a natural way of producing these kind of molecules and other complicated things. If we don't know the makeup of the atmosphere, we don't know, does it have oceans? Does it have volcanoes? What do these planets have?
It is a Haitian world. That's my understanding. They found traces of water vapor in the atmosphere or something like that. I don't quite understand it, but
yes, I think that the correct quote is "it might be."
Okay, I'll stop saying it is. It might be.
Okay, I'm going to make a suggestion for you and your listeners. Is you can go and check out a colleague of mine who knows more about this. His name is David Kipping, and he runs a YouTube channel called Cool Worlds. And
I've heard of David Kipping. Yep.
Yeah. So on that channel, he recently made a video, whereby he gets together the lead author of that paper that made the discovery and their biggest critic, and he basically chats with both of them about what the real meaning is here. And at the end of it, it's not for you to take away this message or that message, that there is this or is that. But I think it basically cuts to the main point here about the uncertainty in the science because you're trying to do something at the cutting edge. So I recommend you check out that video. Again, I don't want to rain on parades. I know that people find these stories very exciting, but it's worthwhile taking a look just to understand where the professionals stand on this kind of thing.
Yep. You strike me as a realist as opposed to someone who kind of just gets carried away with these types of things.
Oh, you have to be. It's in science. Honestly, one of the worst sins you can commit being a scientist is essentially pushing your data too hard and claiming that you're seeing things in your data. So this is part of the reason that one of the things that's happening in science, it's not completely blanket, but it's becoming that way, is that if you find something interesting, is that you make your data public. You say to everybody, right, go for it. Confirm me, deny me, whatever. Just take the data and do what you would do to it. And I think that is a really important aspect because it allows you to check that you weren't biased yourself when you did the analysis. Right? You've got to be very careful that you didn't bring your own biases to the table. So, I think science is very much about being a realist, but it's also, I'm going to have to try and choose my words carefully here, right? You also have to have imagination, right? You do have to think of the possible and the maybe the fantastic and wonder if it has a place in your scientific theories. But we are always grounded by reality, right? There's no point in me saying that the moon is, carried in its orbit by pink unicorns, and then saying, "Oh, you can't test that. You can't ever test that there's pink unicorns there because they're magic and invisible." That you're not doing science anymore, right? We have to be grounded in reality. If I'm going to come up and say to you, I think that this is what happens, then the first response should be, well, what's the consequences? How do we tell that that's the case?
Yep. Yeah, for sure. Well, I'll have you know you have completely rained on my parade.
Oh, sorry.
But it's fine. I wanted you to tell me, yeah, we found aliens, but it's all good. Yeah. It's all good. Yeah. Oh, well, look, what about in terms of, let's apply that mindset to something else, right? And I'll ask you straight out. Do you believe, I don't mean to get too pothead on you, right? But do you believe that we have been visited? Would you say that? Just tell me what you think. I'm not going to justify my potheadness.
Okay. So I'm happy to justify myself. I would say that we have not.
You would say you have. Okay. Yep.
Yeah, we have not. So look, and I was recently in New Mexico, not that far from Roswell.
Yep.
I mean, you know, I what again. I'm trying not to rain on parades. So
rain on them, ruin all of our days.
No. So one of the areas that I've worked in is this question of the habitability of the universe, right?
Yeah.
What life. You want there to be life out there, but you want more than there to be life out there, right? You don't care if there are worlds with pond scum everywhere, but you want intelligent life. I can tell in the picture behind you, you've got little green men there, so you want intelligent aliens there, right? And so the thing is that if there had been intelligent aliens in the past that can fly between the stars, they would be obvious, right? They would be obvious because the cheapest form of energy in the universe is starlight. You've got natural nuclear reactors working away, and as we're finding out here in Australia, right? Solar power, that's the way to go. So, if you've got a civilization that can start to fly between the stars, then they would need lots of energy, and the easiest thing to do is tap into starlight. So there's this notion that alien civilizations would build these things called Dyson spheres, basically giant solar panels that completely wrap up a star. But what that does is that takes that starlight and it turns it into waste heat. It turns it into infrared, right? That's what it does. And so if we had civilizations out there that could do that, they would be obvious. Firstly, we wouldn't see stars, and there'd be regions where it would all just be infrared rather than stars, etc. And we see nothing.
I mean, we can't. That seems like a pipe dream to us, and we're an intelligent species. Dyson spheres. I mean, how much material would you need to build a whole shit around the sun? You know what I mean?
Well, so this is an interesting question. You don't actually need that much, right? You're talking about let's take a planet like Jupiter. Right? There's plenty of matter in Jupiter which you could siphon off and start turning into solar panels, right? I mean, you'd have to be considerably more advanced than we are now. But let's think about this, right? We want everything to happen tomorrow, but this might not happen. We might not have the skills for another 10 million years if we survive that long. But if we can, big if. If we can start to engineer planets, we could start to build Dyson spheres. So this is the thing. So you can basically suggest that maybe there were aliens in the past and they never bothered going exploring, but that would seem very weird, wouldn't it? I mean, would you think that every single alien planet that we have, they all decide that they wouldn't go exploring? You just need one to decide to go and explore. They can start to colonize the galaxy, and it doesn't take long to colonize the galaxy. It takes 10 million years, right? I mean, we can calculate that.
I'm aware of this theory. So what's the name of the I forgot what it's called. Where it's like, where are they? If there's aliens out there, where are they?
The Fermi paradox.
The Fermi paradox.
That's right.
It.
Yes. Yeah.
And it's a good question.
Well, it is. I've read many papers on the Fermi paradox. I've read many potential solutions to the Fermi paradox, but none of them really work. Right? So some people have suggested that maybe they don't go traveling. Some have suggested that maybe they all just go to sleep because they're waiting for the future of the universe when energy is going to be cheap or whatever. But in general, right, we have to remember that our Milky Way galaxy has been around not for 10 million years, but for 10 billion years. And so if there were civilizations in the past, they would have had plenty of time to occupy the galaxy. But there is no sign of them, none whatsoever.
But we also take into account the vast distances in space. I'm sure you're aware of this. And like, it's our biggest roadblock. You know, we're struggling to get to Mars. I mean, I think Elon Musk will get us there just quietly, but like, how are we going to reach? You got Proxima Centauri. That's what, 4 light years away. And is it with our current technology? It would take us tens of thousands, if not hundreds of thousands of years. Am I right in that?
That's right. But you have to remember that powered flight is 120 years old.
Yep. That's a good point.
We have barely
infant.
dipped our toes in the water. And the other thing that you have to remember is that we've made a lot of progress and we can still make a lot of progress. But at the moment, we're more focused on building aircraft carriers than antimatter engines, right? So if you have investment and you allow people to work in these things, again, we don't know if there is a solution or where the solution will come from, but it doesn't mean that we won't do it in 1,000 years from now. Right? Yeah. Now, to you and I, 1,000 years is ridiculous. But, you know, human civilization... In the grand scheme of things. Yeah. No, it one revolution around the Milky Way for the sun is 250 million years. That's the kind of time scale that we talk about when in astronomy, right? So it's millions to hundreds of millions to billions of years. So you have huge amounts of time. So this is the thing. This is why. Again, I recently visited David Kippin over in Columbia Uni, and we discussed this, which is why him and I think we agree that there probably aren't other intelligent civilizations out there. It's just
what?
We don't. Yeah,
you don't think there are at all?
No,
just because we haven't seen them.
Just because they would be obvious. I have a friend who is he's a historian, and I was talking to him, and he said, you know what the biggest sign of past human civilization intelligence was? And you might, what would you think? You might say ancient cities or whatever, right? It's not. It's rubbish tips, right? Every human society has just left crap behind them, and we would expect if the galaxy was colonized that there would be signs of it, right, left over, and we don't see anything.
There's already shit around the Earth, right?
Yeah,
We've got a lot of space rubbish.
That's right. We're very good.
A lot of shit just spinning around us. Yeah,
dumping crap everywhere, right? So and again, there's a colleague of mine down in at the ANU in Canberra called Charlie Lineweaver. He has this thing which he likes to talk about called the Planet of the Apes fallacy. And the Planet of the Apes fallacy is we have this assumption, right? We think we're pretty evolved, as you said. We think we're intelligent, all this kind of stuff.
No, we're not. The Kardashev scale, but that's what we should refer to.
But what he pointed out is that imagine that we went extinct tomorrow. All humans vanished. Now, we think that another creature will evolve into that intelligence niche, right? You know, this is what the Planet of the Apes movies are, right? Is that the apes take over, or the cockroaches, or something. But he also points out that dinosaurs had 150 million years to evolve intelligence, and they didn't bother, right? I mean, they just didn't bother. So it might not be that intelligence is evolutionary as beneficial as we like to think. And as you know, it's probably doing the opposite, given the degradation of the world, nuclear weapons, etc., etc. Intelligence is not necessarily the best thing for propagating your species into the future. So it might be that if we disappeared tomorrow, that there would never be another intelligent creature like our level of intelligence on the planet, right? I mean, dolphins are smart, but they don't bother building nuclear weapons. Right? So if intelligence is a rare thing here on Earth, then why wouldn't we expect it to be a rare thing through the universe? Right? We pride ourselves on our intelligence, but it doesn't mean that it's like this is the goal of evolution. The evolution doesn't have a goal. other than for your species to keep propagating.
Yep.
I realize I'm just raining on everyone's parades here. We should really talk about something positive.
You're right. You're right. Look, one more bit of pessimism for a lack of intelligence on this planet. Can you imagine if we weren't the only intelligent creature on this planet? Like, you look at, we're fighting each other. We're out here trying to blow each other up, and you know what I mean. Like, imagine you bring other creatures into it.
Well, this is something I definitely have thought about over the years, of course, because we're the last of our family tree. But in the past, we had our parallel cousins. So we had the Neanderthals, the Denisovans, and those, and we don't know what their intelligence was like. We don't know what their consciousness was like, etc. We do know that we interbred with them. Anyone who's got European ancestry has 3% Neanderthal DNA. So
yeah, right.
So it's one of those questions. Did we exterminate them? Did they lose due to the inability to basically match our civilization because we got ahead on the intelligence sort of scale? We don't know, but I think it's an interesting question, right? I mean, what the interactions between Neanderthals and modern humans was like.
Yeah, that's something I've never even thought about, to be honest.
I mean, this is again, it's a very interesting question. It said, if you look over our family tree in Asia, there was the Denisovans, and so like the Asian populations have their lost cousin, which are part of their DNA, so they interbred. And I'm not an expert in this topic, but there are people tell me that there are other trace amounts of DNA in other groups, which suggest there were other populations that also interbred and went extinct. So I think it's kind of fascinating what the world would have been like, right? Neanderthals died out not that long ago.
Yeah. I think time is misconceived a lot. There's a lot of like, I can't give you examples off the top of my head, but people don't realize how, in the grand scheme of things, how short the time span is between big historical events and even like how far humans have come. Like, I'm not really explaining it that well, but you understand what I'm saying?
Absolutely, because I mean, this is definitely something that I have given a bit of thought to, right? But the modern humans left Africa, let's say about 100,000 years ago. Modern civilization, is between 5 at a push 10,000 years. So that means that, like, between leaving Africa and the start of modern humans around the world, starting civilization, etc., 90,000 years, right?
Yeah.
That's a long time. A long time.
For us.
Yeah. But then, we talk about, when did we separate from the chimpanzees? 6 million years ago.
Yeah. Off its head.
Dinosaurs died out, 60 million years ago. And these timescales, they are immense.
Yeah. 100%. 100%. Look, we'll steer away from the pothead questions. Even though I could stay here for a hot minute, we'll steer away from it for a bit. I want to ask you something. Do you think, because in terms of, in cosmology, thinking about how the universe started, how it's going to end, surely religion gets tied into this a lot?
No?
Because, no. Okay, all right. Explain yourself. How does it not? First, and are you religious? I'm quite curious.
I am not. I am atheist. I'm an atheist, but I have colleagues in cosmology. I wrote a book with a colleague I've written actually 2 books on cosmology. One with a cosmologist who's religious, and one with a theologian. So no, religion doesn't come into it in the sense that it's not a guiding principle to your development of your theories, right? Let me just wind back, and I'm going to. Can I tell a little story?
Tell them.
All right. Okay.
Tell them the story.
So people are very familiar with the name Edwin Hubble. He's the guy that discovered the observations for the expansion of the universe, right? But what's less known is who did the interpretation, right? Who interpreted the data to say that it's an expanding universe. And so Einstein had been working on this stuff in Europe, and he is working with a guy called Lemaitre. Okay. So Lemaitre was the one that said, oh, look, we have an expanding universe, and Hubble's data confirms it. And if we wind that universe backwards, it tells us our universe had a starting date, right? Some number of billions of years ago. So that came from the data. Now, Lemaitre happened to be a Belgian cleric. He was a Catholic priest, basically, right? And he got accused of trying to smuggle religion into science, right? I.e., it was claimed that he was trying to make out that creation of the Bible and the birth of the universe, the Big Bang, were the same thing, and therefore, was religiously inspired. But it's not true. It's not true. That's not what he was doing. He was working with the observations and allowing the observations to basically guide his conclusions.
Yeah. Look, I'm not religious. I've always been an atheist, but I'm very open to the discussion. I'm a big what if kind of guy. You know?
Yeah.
Right.
Yeah.
So there's, and I might squander explaining this, but there's this thing I heard not long ago. It was saying how the universe it's so fine tuned, it needs to operate. Everything it needs to operate, man, I can't even begin to explain this. Everything it needs to operate is like, you just need, man, I can't even explain it. Basically, everything you need is God, essentially.
Okay. So this is something I can explain because I wrote a book on this. So I wrote a book called A Fortunate Universe, Life in a Finely Tuned Cosmos. Myself and Luke Barnes. Luke is a cosmologist at Western Sydney University, but he's a theist, right? So I'm the atheist, he's a theist. So
what's a theist? Just quietly, what's a theist?
It's the opposite of an atheist. So a theist is somebody who believes in God.
Yeah, right, my bad. Moment.
Yeah. So the fine tuning of the universe is this question of, right, if I look at the laws of physics, right? So I've got my, equations of quantum mechanics or relativity, etc. And I want to imagine hypothetical universes, right? So imagine that I want to think of a universe where there are more dimensions of space than in ours. So there's 3 in ours. What if there's 4 or 5 or 6? Or if I want to modify the strength of gravity or the strength of electromagnetism, etc. And it turns out that if you think about these hypothetical universes, then you can very quickly show that these hypothetical universes are dead. They're dead and sterile, right? So, and what I mean by that is that they don't host any complexity. They don't have a periodic table of elements. They don't form molecules, etc., etc. No life whatsoever. So the question is why? Now, some of the theists say, well, clearly these values, which are fine-tuned, must have been fine-tuned by a fine-tuner. And that fine-tune...
Yeah, that's what I'm trying to say, yeah.
And that fine-tuner is either, God or Odin or Buddha or, whomever, right?
Yeah.
But that's not the only solution to this problem, right? There are scientific solutions to this problem. And the one that I favor is that our universe is not alone when it comes to being a universe. That as well as our universe, there are other universes out there in what's known as the multiverse, right?
Oh, now, I love that you say you're taking me down this road. I didn't even have to ask you about multiverses. Come on.
Yeah. So, but I'm going to, again, be careful with my words here, right? So the multiverse is it's a hypothesis. It's a suggested solution to a problem, right? So we don't know if we are part of a multiverse, but I think that this is possibly where the solution lies. And essentially what you've got is that if you've got, like, imagine you've got a huge number of universes, like a ridiculous number, and each of these basically when it was born gets like fingerprinted with its own set of laws of physics, then in most of those universes, they'll be dead and sterile. But every so often, the laws of physics will be just right, just mixed correctly for complexity and life to form. And we shouldn't be that surprised to find ourselves in a universe that looks fine-tuned, because we wouldn't be in any of those other universes, right? We couldn't exist there because there's not the right number of dimensions of space or whatever. So yeah, so the fine-tuning argument, some on the religious side say, oh, it's evidence that there must be a God. Whereas on the scientific side, there are solutions based in possible physics that we could uncover in the future.
There's a couple religions, and again, I'm not religious, but there is a few religions, and in my opinion, Islam is one of them. Very fascinating religion, I think. In the Quran, some of the miracles that are mentioned in the Quran are like explaining how the universe began, explaining the Earth's atmosphere. Do you know about any of these? And I'm sure they can be explained, but it's kind of fun to think about.
So I am not an expert on Islamic texts.
Yep.
I wouldn't be surprised if there's a bit of interpretation going on here. I mean, I doubt that it.
Sure.
I doubt that it describes the expansion of space-time of the universe and inflation and the formation of particles, and it doesn't have any of that, but it might have a very broad brush kind of picture, not too dissimilar to the Christian Bible. Let there be light. Oh, well, that sounds like a big bang, doesn't it? So yeah, I mean I think and I think it's fine. Again, I'm not a religious person. I'm not going to tell people how they should interpret the text in any way that they want to. But for me, I don't find that as convincing evidence that the Quran or the Bible or whichever book you want to choose is a science book. I think religions are more around discussing your spirituality and morality rather than trying to teach you organic chemistry.
Spirituality.
Yeah.
Would you say there could be something to that, something to spirituality, as opposed to believing in a man in the sky is looking over us kind of thing? Do you think we are part of the universe in a way? And I don't know. What do you think?
Well, look, undoubtedly we are part of the universe. But we are more parade raining. We are an inconsequential part of the universe. So I'm gonna lay my cards on the table here, right? Before we go all kumbaya, etc. So spirituality, etc. What people want to believe that makes them feel whole or whatever. Whatever John Lennon said, right? Whatever gets you through the night, okay? It's fine by me. So spirituality, etc. If you have a sense that you want to have that feeling of belonging and something bigger, that's perfectly fine, right? It's not for me to tell people how to live their lives. But it's not science in the sense that it doesn't tell us how the universe works. It doesn't guide us in the way the universe works. And I know there are individual stories. Some people will tell you that their spiritual side does guide them in their day-to-day, but it's not like the driving force in science is that spiritual aspect. I said it's grounded in what you detect with your instruments and your telescopes, what you see in the world around you.
You believe in an afterlife?
No.
Really? So that's something I struggle to wrap my head around. Like, we just die and then it's nothing and then it's nothingness forever.
Well, I mean, the universe was around for 14 billion years until I came along, and I was nothing then. I mean, I know that this sounds like a very negative kind of picture, but I don't think it is, in the sense that I think we should be grateful that we have this brief moment in the sun, right?
100%, 100%.
There are 100 billion trillion ways of being dead, and so the fact that you've had a chance to spend time on Earth, and I know that it can be very stressful, it can be very ugly, and all this kind of it. But as I said,
it's a blessing. It's a blessing.
Yeah. Yes. So but I understand. Well, let me rephrase this again another way, right?
Yep,
so
yep.
we have our time in the sun, which I think is great, but we tend not to think about us, right? In the sense that my body is mainly water, hydrogen and oxygen. That hydrogen in my body, that was created in the first instances of the universe. The protons were. The oxygen in my body, that was once in the heart of a star, right? I mean, it was like it was created as a star was burning, a star much bigger than the sun. If I take something like wedding ring, gold ring, this gold was created in some of the most violent events in the universe, when neutron stars and black holes, etc., stars exploded to produce this stuff. Okay, and then after I'm gone, it gets recycled and it will go into the next set of stuff. I think that's kind of amazing. We think we some sort of, I don't know. Do we think we're unique, or that I was created out of perfect stuff? No, I'm just recycled stuff from the universe, as is everything else. And I think that's
fine-tuned, but
still fine-tuned, but
yeah.
But
a lot had to happen for us to be here.
Yes, but don't you think it's kind of cool? Like the iron in your blood used to be in the middle of a massive star, and maybe has been in the middle of several massive stars.
Yeah, it's a head fuck. It really, it's a head fuck if ever I've.
Yeah.
Are you there?
Yes, I think we froze there for a second.
Sorry.
It's okay.
No, I'm still here. Yeah, no, look, it's a lot to wrap your head around for sure.
Yes.
I've heard that that's not even a theory. That we know that, right?
Yeah. I mean, we know where elements are created, right? So we've known about the elements that were made in the Big Bang. We've known about those since the 1940s. And then in the 1950s, we worked out how stars really worked. The collision of neutron stars to make heavy metals, etc., that was more recent. But yeah, we understand, right? When you want to create a heavy element, you need energy, and that energy you find in big stars. So there's nowhere else in the universe that could forge iron, right, other than the hearts of stars. So that's where we've been.
So, in terms of, I want to know if you know much about France's nuclear fusion reactor, which I read the other day is reaching 50 million degrees Celsius, which is a lot hotter than our sun, but it's still not enough for what they're trying to accomplish with it. I don't even know what they're trying to accomplish with it. This.
Okay, so let's start with nuclear weapons, right?
Yep.
So it's this year is 80 years since the end of World War II, which means it's 80 years since the first atomic explosions. Now, those atomic explosions were powered by uranium and plutonium. So these are heavy elements. So they're big, fat nuclei of protons and neutrons. And you break them apart. And in breaking them apart, you can release energy. Okay?
Yeah.
So the bombs that they had for Hiroshima and Nagasaki, they were kiloton size. So they were thousands of tons of TNT. Yeah? But then into the 1950s, people realized that there was a bigger source of energy. So these are what's known as the fusion bombs. So when you break elements apart, it's fission. When you stick elements together, it's fusion. So what you want to do is you basically want to do what the sun is doing. You want to take protons and you want to get them to stick together because that releases energy, right? Now, the problem is that that's hard to do because these things, they're charged, they carry positive charge, and so like magnets, they can repel, and so you really need to get them very close, okay, for them to latch together, but they tend to push each other apart, okay. So how do you push them together? Well, the solution that we have on Earth is in a thermonuclear bomb, is that you basically squish them together by put them essentially inside a nuclear explosion. So when you build a hydrogen bomb, you basically fire off a uranium or proton bomb first, which can squeeze all this stuff together so you can get this thermonuclear reaction, which releases a lot more energy. So the biggest hydrogen bombs are up to 100 megatons, 100 million tons of TNT. So they're much bigger than the bombs that were dropped in Hiroshima and Nagasaki. So if you can stick light elements together, you can release a lot of energy. And in the sun, it does it by having the material very hot, millions of degrees, and very dense, right? The center of the sun is squeezed really, really hard. We want to do the same on Earth, right? Because currently our nuclear reactors work via the breaking up of uranium and plutonium into smaller things to release energy. But we would like to do the opposite because firstly, uranium and plutonium, when you break them apart, they leave radioactive stuff behind. Whereas if you can take basically hydrogen and stick it together, you end up with helium, which is just an inert gas. So it's a clean thing. So we want to do the same thing on Earth, but we can't get we can do it on Earth in a bomb, but we want to do it in a controlled way. So we can't actually get the densities high enough because we can't push this stuff together in any way. So what you try and do is to get things hot enough to make the collisions close enough that you can actually get protons to join with protons. It's a bit more complicated, but that's essentially what you want to do. So you want to get a fusion reactor and you want it to be stable. And the problem that they've had is that it's basically been impossible to make these things stable and produce constant energy.
Now, if we can achieve this, do you think we would go down the route of making big fuck-off bombs, or do you think we would go down the route of providing energy for the entire world?
We already have the bombs. We already have the bombs based on this, so they won't make them any bigger. It will produce lots of energy, and it will be cleaner than coal and nuclear, etc. It's not perfectly clean. There are some issues around it, but it's hard. I'll tell you what the hard part is, right? If I give you, as you said, they want to get material up to 50 million degrees. If I give you material of 50 million degrees Kelvin, what do you put it in, right? Because it's hotter than anything. It would melt all metals, etc. So what you have to try and do is you have to try and hold it in the equivalent of a magnetic bottle. So you use magnetic forces to hold it in place. Now, the problem that you have is that you can put those magnets there and they have to be very precise, but then you have to get your protons moving around inside your magnets. And those protons, which are charged when they move, they produce their own magnetic fields. So what you tend to find is that you start off with a nice, smooth distribution of magnetism. And then as you start to run this thing, the magnet you get what's known as instabilities. The magnets basically flop all around until you basically lose the ability to hold that stuff together, and it just all dissipates. So they haven't been able to hold that stuff together long enough to get out more energy than they put in to try and hold it there in the first place.
Yeah, well, I don't even talk about. I can't wrap my head around that for a second, to be honest with you. And I didn't know much about the nuclear fusion reactor before I read about it for the first time the other day.
Yeah. They've been trying for a
But
long time.
it's an interesting, yeah.
I
For what
think
reason? Like,
uh,
what's the actual goal at the end of it? That's what I'm trying to wrap my head around.
the goal would be that you would produce essentially unlimited amounts of energy,
Energy.
right?
Yeah.
And that unlimited amount of energy would be essentially clean.
Okay. So
Right?
does that also mean that with that much energy, back to the pothead questions, the Kardashev scale that I mentioned before, that's about
Yep.
harnessing energy from your sun, which we
Yep.
obviously can't do. Well, first we need to, right now we're not even a level 1 on the Kardashev scale, right?
No.
And to reach level 1 is we got to harness all of the Earth's energy, right?
Essentially, yes.
Yeah, okay.
No,
So once we can perfect this nuclear fusion reactor, do you think it's possible?
Oh yeah. Fusion is possible. We know it works.
So we think that this'll be achieved.
Yes, but I could tell you if it's going to be 10 years or 100 years, right?
Yeah.
Because there are technological challenges, engineering challenges that have to be overcome. There's nothing fundamental that says you can't do this. The issue is around building these things. But it's the same as, if you think about it, going from a propeller plane to a jet plane, right? Jet engines, when they first built them, the German jets in World War II, you could only run them for a few hours, or before they essentially disintegrated. People realized what kind of materials you needed to use. And now we have jet engines which are highly reliable. You can run them over and over and over again. It just takes time for people to experiment and to build and extend. We should be able to get there in the end. This is why there's so much effort around the world that people are trying to do. Is it's a possible, and it would be very cheap energy if you can get it to work.
Yeah. Something else I want to talk to you about is how you think AI is going to have an impact in astrophysics, cosmology, just the study of all things interstellar and
Yeah. Well, it already is in that in many ways it's increasing productivity in the same way as it's doing in many other fields, right? So it is helping, searching for what's already been done. We write a lot of computer code, and so AI is very good at generating that code. I mean, I don't mind AI, but I do worry that it's a bit of a flash in the pan due to its sheer energy use. Again, going back to that question of, So that question of generating energy, what people don't realize is that when you build an AI system, you're building what's known as a large language model. And what you have to do is you have to basically pour in all your information, and then you have to basically optimize the thinking of the AI system, and that requires huge amounts of energy, huge amounts of data storage, etc. So and my understanding is that like the big companies are now talking about whether or not you need your own nuclear reactor to run your AI center, right? So to provide enough energy. So it could become essentially prohibitively expensive in the future to use AI as much as one would want to use, and you have to potentially look for alternatives that don't use as much energy. So, I mean, I don't know if you know this, but like the computer inside your head, right? That runs on a few watts. So what we want is computers that run in a similar kind of scale to the human brain, rather than having to use gigawatts of energy to train your AI system. So I know that there are people who are working on what's known as synthetic intelligence, where instead of building basically a software version of a brain, You basically try and build a hardware version. You try and build a thinking machine. And that can be very, very low power compared to what goes on in the AI systems. So, I think this is a very fast moving field. I think these things are all going to change very rapidly over the next few years. But already people are using AI in astrophysics as much as they are everywhere else, just as that productivity booster.
Yeah. I think AI is kind of going to, in the same with space travel, like we were saying before, the vast distances. I think AI could potentially kind of help us get there. And the same with, you're talking about how much energy is needed for AI. AI could kind of build itself in the most efficient way possible. Do you know what I mean?
Well, yes. I mean, I do have this question about how creative AI can be, right?
Yeah.
So if you listen to
You
some
can
of
still
the
tell it's not human. You can still tell that it's a robot, and you know what I mean, like.
And the other question in there, of course, is that can it do something original, or does it just regurgitate back something that it's
Well, I mean, they got AI writing songs, making movies. People are doing some crazy shit with AI at the moment.
I understand. And I can understand that if I ask AI to write me some music in the style of Mozart, then it can do it. But if I ask it to come up with something new that would appeal to me, what is it going to do? So it's said. Some people say that it lacks that central creativity. It has some creativity, of course, because it can pull things together and put things together that you might not imagine. And I do believe it's going to be a boon for like movies, etc. I mean, it can't be any worse than most of the scripts that Netflix currently uses.
Disney's dropping shit, man. At the moment, what Disney's run out of ideas.
I find it amazing. I really do, that how bad some of these things can be.
Oh. No, just quietly. No one asked for another Toy Story. No one asked for Ice Age 6. No one wants any of this. Just quietly. Like, go on. Sorry.
So yeah, I do think that it will make a difference, and I know we will get the first completely AI movie soon, complete script. They'll generate the images, they'll do the voices, etc. And it'll look terrible, and we'll all laugh at it. And then 10 years down the line, it'll become the norm. And I think that maybe then, maybe we'll see something new, something different, but we'll have to wait and see.
Yeah, it's still very early days for AI as well.
Yeah. Which is why, I know some people like to write these things off, but I think you've got to give these things time, right? And as you said, the changes we've already seen, the impact it's already having, has been quite significant.
Yeah. Crazy. We got a crazy future ahead of us, eh?
Absolutely.
Well, Professor Geraint Lewis, it's been a pleasure having you on, mate. Had good fun talking to you. Even though you rained on a lot of my parades, it's all good.
Yeah.
I'll let it slip.
Yes. As I said, I'm really sorry, but I have to be grounded in reality, and
that's all good.
Rains on parades.
I need people like yourself to bring me back down sometimes, because I'm seeing K218B. I'm starting to think they're on their way here, but that's all good. Look, we'll need to get you into the studio sometime. Yeah, it's been great talking to you, and we'll do it again for sure. Thank you very much.
Thank you. Bye-bye.
Thank you very much. Take care of yourself, mate. Bye-bye.